Austria. And yeah, I've been a juror at the IYPT for the third time now. And it's my first time as a chair. I'm very happy to do that today. And first of all, I want you to introduce yourself, the team. So we will start with the team Chinese Taipei, which will be the reporter in the first round, the first slide. Yeah.
Okay. Hi everyone, I'm the team captain from Team Taiwan, and this is Oscar, this is Andrew, this is Justin, this is Kai, and you can call me John. And we hope to have a great fight. Thank you.
So now I would like to ask Team Switzerland to introduce themselves.
Hello, so we're Team Switzerland. Those are our two mascots. So Super Mirku, Super Mirhue, and I'm Harold Martinson.
Yeah, I'm Mattis.
I'm Joe Museri.
I'm Rachel.
And I'm Shimon.
And finally, we got Team US to introduce themselves, please.
Thank you. Hi, my name is Bridget Whitfield. I'm the team captain for USA. We have Peter Hugh, Jimmy, sorry, can you Wonka Vic, I'm so sorry. Ivy Wong and Valerie Wakeman. Thank you.
Okay, so then jurors, please introduce yourself. We will start here, please.
Hi everyone, my name is Adam Kadlicic. I've been a team member in Team Hungary like a few years ago now, and now I study at Stockholm University. So I wish everyone a very nice day.
Good morning to everyone. I'm Grigoria Kisea. I'm from Greece. I'm a team leader for Team Greece. It's the first time to be a juror this year, so I'm very excited. And I wish you the best of luck.
I'm Marco Sasso. I'm a mathematics teacher from Italy. Last year I was team leader for Italy, and now I'm your juror for today.
Good day, so I'm Parth Thanarakit from the team Thailand, and I'm doing research in quantum future in quantum simulation from the Korea Airline Institute of Science and Technology. I'm also part participant of IYPT, and now I'm the reviewer for the IOP Institute of Physics. Wish you a good luck for today.
Thank you very much. So I now want to ask all the teams if they already checked the connections and everything will work fine.
You have to check.
You have to check, okay, then take your time. Okay, so in the first stage, Team Chinese Taipei will be challenged from Team Switzerland and reviewed by the Team US. So I want to ask the Team Switzerland to challenge the reporter now.
Hello, so I challenge you on problem number 6, dripping faucet.
Yes, sir.
Dripping faucet number 6 is accepted. Put all the team members in action, write their names on the board, please. Start whenever you're ready.
I can start now. Hello everyone, I'm a reporter from Team Taiwan presenting problem number 6, dripping faucet. A leaking faucet can develop interesting dripping patterns depending on the water's flow rate. And I have to investigate this phenomenon and study how it depends on the relevant parameters. For the faucet parameters, we'll have the faucet diameter and the water flow rate. Then for the fluid properties, we'll have the surface tension and viscosity. And the interesting dripping patterns in the problem statement is talking about the time interval, which is the time between the drops. So here are the contents for the day, and I'll start with the setup and the observation for this phenomenon. So the setup starts with the water tank, which I control it to have a constant water level by refilling it. And this will generate a hydrostatic pressure, which pushes the water out. And it will push the water out inside this tube. And this tube is a long stainless steel tube, and then I put it behind a light source and a camera. I measure the flow rate over time, and we find the variation to be very small, to be less than 2%. So I have an accurate flow rate control. And I measure the flow rate by weighing the weight of the water collected. Then here are the drop formation observation. So first, we see the pending drop will oscillate like this. Then, after the water flows enough, it will reach a critical mass as the thin neck will form above the drop. Then, the primary drop will detach. Then, this liquid column will separate into some satellite drops. So here is the effect of flow rate. So when I increase the flow rate, we see these different values. And under a critical flow rate, we see it being drops. And over a critical flow rate, it will be a flow. Then if we take a picture before the detachment, and we see the flow rate does not change the drops volume that much. They all remain the same under different flow rates. So we see the drop volume doesn't vary with flow rate. But the thing it does vary is the time interval, where this is the time interval graph. As we increase the flow rate, we see the time interval getting decreased. And it will go from one single time interval into these interesting and non-irregular patterns. So let's talk about the qualitative explanation on why is there interesting patterns. So here's the drop formation. When a drop forms, it will have gravity and surface tension. And this surface tension will give us a critical mass of the volume of the water that the surface tension can hold. Then for necking phase, because of the Laplace pressure difference on the surface tension and causing the curvature to be different, and this neck will be separated into one pending drop and one primary drop. Then here's the satellite. So the remaining liquid column will try to minimize its surface energy. So that's why sometimes it will break up into little satellites. Then the pending drop will go back due to a restoring force and causing an oscillation. So here is how the pending drop will oscillate while the drop volume increases. So the first case is a single period where we see the oscillation of height to time. And we see the single period, they have quite similar oscillations. So we think they have the same initial conditions while detaching. But the second phase of a doubling period, we look at the height to time graphs, we see two different kind of trends. So one is where it will detach while the droplet is oscillating upwards, and one is detached while the drop is oscillating downwards. And these two different initial conditions causes the two different time intervals. Then for a chaotic region, it sometimes simply just breaks off from the liquid column. So even no satellites will form in this chaotic region. And the detach and oscillations will change the initial condition of the drop formation, which results in the interesting drifting patterns. So now let's talk about the time interval and the drop volume. So here's the time interval under different flow rates. As you can see, as flow rate increases, the time interval decreases. And in low flow rates, we see a single time interval. At this point, we see two dominant time intervals, and this we can see a quite messy time interval, which is quite irregular. So I have a Young-Laplace equation to calculate the static shape of the drop. So by Young-Laplace law, we can have the two curvature. One is along the drop profile, and one is along the drop circumference. Then accounting for static pressure caused by this height, we could get this expression here. Then we'll use non-dimensional units of capillary length to change the units, and we could get this final differential equation. So if we plot this differential equation, we could get these different drops as I have different volume inside. So we could actually plot the drop length under different volume. So the solid line here means the stable region, which we can see experimentally. This is an experiment background, and I overlay the simulation, and this is a possible conditions. While dotted lines means an unsteady solution, which as the next, because it will start to separate the next second. So for this one, for example, it will separate, and this one also. And this is called a saddle node purification. And by this, we can calculate the critical volume for a drop to be this critical line. So after knowing the critical volume of the droplet, we can get this simple analytical form on the time interval for steady drops. So with this line, we can accurately predict the average time interval for the drops. And I think this works good for the single period, but what about the doubling and chaotic region? So as I mentioned, the detach and oscillation causes the different initial conditions. So we can analyze it as the drop formation. First one is the drop formation time scale. The second is the drop oscillation time scale. And if the ratio is closer to 1, it will be a little bit more unpredictable because the oscillation is significant, causing the detachment. So from the reference, I was able to get the volume of the drop and then use the Lagrangian for the fluid motion, accounting for kinetic, gravity, and surface energy. Then they simplify it into two-dimensional motion near pinch off, as the two motion I was mentioning about is first is feeling the drop, then is the oscillation near pinch off. And this is the equation that this gives us. Then these black dots are the simulation of time intervals. And take this one for example, we can simulate the different time intervals for different drops and get a return map. But we can just see how it predicts, and this is the region that it predicts from the results we have. So we can see it agrees good with the critical values. So then let's look at the return map. So now I have a setup without refilling, so the water level will decrease over time. So it is a continuous dynamic fluid decrease. So this is our return map. So as this is the color is the fluid. So as the fluid decreases over time, it will go from this part to this part. And what the return map means is the time interval for this drop and the time interval for next drop. So this shows a pair of time intervals where we can use to analyze the dripping patterns. So along the red line, it will be the periodic phase because the first drop and the next drop will be the same interval. So if we take this point, we see it is quite close to the middle line, and this is the periodic condition. Then for doubling period, we see it will separate along the line with two parts as the two different time intervals. And this is caused by the difference in the initial condition of the oscillation I was mentioning about. And finally, it is the chaotic region where we see mess in the big region. And yeah, it's spread out all over the middle and the sides. And that's where the chaos happens in the higher fluid region. So here, the dotted lines are the theory prediction from the fluid motion simulation I had. And these colors are mentioning the different periods. And we can see the blue regions are from the experiments. So we see the experimental range, which is a blue line, agrees well with the black critical. So we're able to get the theory and experimental critical for different phases. Now, and we also investigated the drop and satellite volume. So in this condition, I will see two different satellite drops. And we see the second satellite drop will be smaller than the first one, and they both are order of magnitude smaller than the main drop with around 5%. Then let's look at the relevant parameters. So first is the tube diameter relation to a drop volume. So this linear line is the linear estimation of the volume and the gravity and the surface tension. And the blue dotted lines are the Laplace pressure. We see both the simulation and results deviate from linear. And this is because in larger diameter cases, we see gravity is a lot bigger and it's more dominant as surface tension, so the drops won't fill up the faucet. So you will see the drop is smaller than the actual diameter of the faucet. So if we plot the 3 mm diameter, which is a smaller one, we see it has this trend, which is the green dots. And so first general trend we see is it will have a smaller time interval due to a smaller critical volume like this. Then we see the doubling occurring in lower fluid. This is because the time scale for drop formation decreases due to the smaller critical volume. So the doubling for the smaller diameter case starts as this fluid. And also in the higher fluid, we see it goes back to periodic. This is from the video we could just see it just the drops all break off from the same position of the liquid column. The next parameter is the fluid viscosity. Why use the glycerol and water mixture? And this is the experiment. This is a formula I find about the viscosity. And we find the viscosity to be 6 times, and the tension only is 95%. So I believe we could investigate the viscosity this way. And we see the orange dots are the higher viscosity cases. So first, we see a general trend of a bigger interval. This is because in higher viscous case, it will take more time for the droplet to pinch off from the neck. So it will have an additional pinch time. The second one is it will start to double in the higher flow rate over here. This is due to the drop oscillation time scale gets decreased because in higher viscosity cases the oscillation gets damped out. Also, interestingly, we're able to find some 3 time interval phases in a higher viscosity. Now, finally, let's look at the flow and hysteresis. So here's the flow when the flow rate is big enough. So it is a linear flow, as the Reynolds number is smaller than 400. And we see from the end, we see the same breakup phenomenon like this, as it will also have a primary drop and satellite drop. And the reason why it will break up is also due to a Laplace pressure difference, as the water from higher pressure will flow to a lower pressure, which separating the liquid jet. Then here's the flow and dripping transition. So when we increase the flow rate, we will go from periodic, then to doubling, to chaotic, to flow. When we decrease the flow rate, we see the flow region getting extended. This is due to when you increase the flow rate, you need to overcome the Laplace pressure, and you need to build enough flow velocity. While decrease the flow rate from flowing to dripping, you have to break the flow inertia. So that's why when you want to make the dripping into flowing, you can help it to build the Laplace pressure. And if you want flowing to dripping, you need to break the flow inertia. And this can be transitioned with the same flow rate back and forth. So in summary, the Laplace pressure difference and minimizing surface energy causes a drop formation with surface tension and gravity. And for the effective flow rate, we investigated the time interval under different flow rates and the return map. And we have a Young Laplace for a static shape and time interval for steady drops. And we have investigated the relative parameters of diameter, viscosity, and investigated the case of the hysteresis. And the reason to cause the patterns is the difference in initial condition.
Thank you.
Yes.
Question from the opponent.
Thank you very much for this beautiful presentation. Could you please go to slide 18? How did you define what is a single periodic and what is double periodic? On the left side, I see multiple dots above each other.
I just see the how many main intervals they have from the intervals graph.
Okay. Could you please go to slide 24? Here too, you mentioned that you have the single periodic and the double periodic, but how did you define it? What is single and what is the double periodic?
Oh, so I just yeah, this is quite the same question as the last one. So yeah, I see kind of like from this graph.
Yes.
So I see this is S1 and this is
okay,
S2.
but could you go back to that graph that I mentioned, slide 24?
Yeah.
How did you define here? You showed different clouds, and how did you define when it was single and when it was double periodic?
Oh, I just see if it's like scattered around the middle line. Yeah.
Could you please go to slide 15? Yeah, no, I'm sorry, that was already answered. Could you please go to slide 29? In this curve, what was fitted and what was purely theory?
You mean about what?
Do you have any fit parameters in these?
I don't know. No.
Okay, and water, could you please briefly explain what the difference between the blue dotted line and the blue solid line is?
Oh, so this line is just the gravity and the surface tension linear relation, and this is the Laplace pressure simulation I was talking about. Yeah.
Okay, thank you. Could you please go to slide 17? You mentioned that we were able to get the critical volume from here. Do you think it's critical? It's the same constant. I'm sorry.
Yeah, it should be constant.
Okay. What assumptions did you make for your theory model? Just briefly. Okay, we'll get back to that.
That's symmetry.
Okay, we'll get back to that in the discussion. Thank you
So
very much.
please prepare your decision. would start this.
Yes. Thank you very much for this wonderful presentation, and welcome to my opposition of problem number 6, dripping faucet. So the task statement was already read. In my opinion, the most important things are that you qualitatively explain the phenomena and investigate when and what types of interesting dripping patterns occur. What I really liked about your presentation was the qualitative explanation. It was really good with the high-speed videos. I really liked that. My main issue was with the quantitative model and its agreement with the data, and I did not have time to get into your assumptions. I would like to get back to that later. And you had I really liked that you had a constant flow rate in your experiments. I like that, and I think that's very important. However, you stated that the data showed a single periodic behavior, even though there were multiple times at the same flow rate, and in my opinion, that is not single periodic. You also defined the single and double periodic regimes in the period plots. For me, it's not clear how you define that. I just saw 2 clouds, and for me, it's not clear how you defined when it was single periodic and when it was multi-periodic. And also, I do not agree with you that the critical volume is constant. And another point is you analyze the viscosity as you add the glycerol, but I'm sorry, I don't know any faucet where glycerol comes out, so I think that's not relevant to this problem. And I would have liked to see some more data points on different flow rates. I really liked your qualitative explanation. I said that before with the high-speed videos. I think it was you did a very good job at explaining that. And you also considered different quantitative models with Laplace pressure and your differential equation and the linear approximation that you did. However, my main problem with your theory was that it did not match the experiments, especially in the single periodic regimes. So you had a theory curve, and you stated that it did not fit well for the multi-periodic data points. However, in my opinion, those were the only ones that fit well. The single periodic data point was not on the line. I think that's a misconception there, and I would have liked that to fit better. And I also disagree with you that the critical volume is constant. I think that's I'll get back to that we can get back to that in the discussion. And yeah, I'd like to invite you up to the stage and begin the discussion. Yes, so during my questions, I didn't have quite the time to get into your assumptions. What were your assumptions for this theory?
It's maybe like it's a symmetry around, it's symmetry, like around the faucet. Yeah.
Okay, so you assume that it's symmetric around the faucet.
Yeah.
That's the only assumption you make.
That's the current one I could think of. Are you suggesting there's more?
I'm not sure. Okay, then how do you have a simulation? You have this Laplace. Can you go back to the theory slide? Yes. What does this predict?
So this predicts. This is based on the angles, and then we could predict. This is the different predictions. So you could predict the static shape. Like this is the video I put a lot animated.
And you plotted this.
It's like this.
No, I think you plotted this somewhere else. You had where you had the linear curve and the one E.
That's for the effect of. So do you want to go to that slide?
Yes, please. Yes, please.
Yeah, here.
Yes. So what did you plot here? What is this curve? Why doesn't it go like? Why is it only here? And what did you plot here? This is the most important.
Because this linear relation just assumes the surface tension is like.
I'm sorry, I'm talking about the dotted line, the Laplace.
Yeah, because this is related to a geometry. So like I think that if you make a case with a larger faucet diameter, where the drop forms, the little angles will be different. So that's causing it slightly deviates from the linear relation. Yeah.
What did you plot here? What is it that I'm seeing?
The critical volume drops.
But what is the formula? What is the equation that you plot?
Here. And it could so this equation could give us
I do not see any volume here. I'm sorry.
Let me it could plot like this kind of. You can imagine it will plot this graph, and it will plot this solid line, and it will reach the solid line, and then it will reach this, and we define this as a critical volume.
Okay, but I do not agree with you that the critical volume is constant. It clearly goes down.
No, these are the unstable solutions. So after it will go back, the solution becomes unstable. So after this So take this point for example, it will simply just separate after it. And
Okay. Do you have any proof that the critical volume is constant?
Yeah, so I have taken the picture from an observation, and we find, I take a picture, yeah, and we see it's quite similar.
What did you measure here?
This is the diameter.
Diameter,
Yeah.
okay. And you say that the volume is constant because the diameter is constant.
Yeah, because you can see from a detachment is close to a sphere.
Okay, I do not agree with you here because I think this one is clearly taller than this drop. I think you should have also measured the height of the drops because that is also playing a significant impact. I'm sorry, I think we got a bit sidetracked here. Could you please go back to to your theory plots? I'm still not quite sure. The one with the Laplace curve, the linear one, and I'm sorry, I still do not understand what you plotted here. I see volume on the y-axis, drop volume, and faucet diameter.
Yeah.
Where is the volume here?
So the volume has to be solved using you have to solve the critical. We have to solve the shape first. Solve the shape first, and then we could get the volume. So this is solving the shape. As you can see, this is the hydrostatic term, and then this is the angles of the curvature because Laplace pressure is related around the curvature of the causing by the surface tension. And so we can solve the shape of the drop then after
Okay,
getting
so
the volume. Yeah.
This is the volume of the drop when it separates.
Yes, critical.
Critical volume. Okay. Could you please go to your setup slides? Okay. Where is is this the water tank here?
Yeah.
And the water, how does this work? The water goes up there?
Yeah. It like look. It has this yellow tube. Do you see it? Go
Yes.
here and then. Yeah.
And what pushes the water up there?
Hydrostatic pressure.
The hydrostatic pressure of the tank down here pushes the water up there.
Yes, it does.
I'm not quite sure how that would work.
So to clarify the methods, we make the tube at initially a downward position, so it was completely filled up with water already.
Oh,
and we
you
put
use
it onto a higher place.
Oh,
So it was
okay.
so after the activation of this valve, it's already filled with water.
Okay,
Yeah.
I think that's a very important point that you, okay. And how do you make sure that the water level is constant here?
Oh, so I have, look, this is usually a plastic tube, is refilling the system, and after overflowing this level, it will just flow out. So it's always full. Yeah.
Okay, and what flow rates do you have here? What flow rates? What kind of example? What regimes were you measuring in? You can stay on the slide.
It is around like 0 to 120 milliliters per minute.
Okay, so do you think that this flow rate would, do you think that you could see the water level variations if you had small deviations in your flow rates?
I don't think, I was just I already tried to prove the flow rate is constant. I vary the flow rate by adjusting the level of this metal tube. Can you imagine? Like, yes, this red one, I move it up and down. And I does not change the constant water level.
Okay, could you please go to the back to your pure theory slides? I think that's the most important part.
Yeah, which, the Laplace pressure one?
Yeah, let's go back to the Laplace pressure one. And the Laplace pressure where you fitted it with this exponential, with your data points. Slide 15, I believe.
15?
Yeah, there was another one, yeah. Yes, and where's the theory curve? Is there a theory curve? Slide 18?
Yeah.
Okay, here. You stated that this curve fits well for the single periodic, but not well for the multi-periodic. I do not think that this fits well. This is clearly outside of the. This is the single periodic. Yes.
Yeah.
Why do you see multiple?
No, so the one I was talking. No, this is probably just some little, because I have you can see it being a little bit transparent. So maybe I have like 500 dots here, and this is only like a few dots out of it.
Okay, but this is still these are still two big blue dots. This is not single periodic.
No. Yeah, but I mean these are single. If you look at these are quite big. We can see two very dark dots, but this is just in the same.
Yeah, I do not agree here. I think this is this would be a point where you could see single periodic behavior, but this is already multi-periodic here too. In my opinion, another critical point that you missed is you have like very few data points in the very interesting regime here where you do exhibit single periodic and multi-periodic very close to each other. I think it would have been very interesting if you varied the flow rate more precisely.
Yeah, but
more
actually,
resolution.
I believe we could draw a critical line around this 40. So below this 40, I think it will all be single periodic.
You think it's all single periodic flow?
Yes, in lower
Yeah,
flows.
I definitely disagree with it. It's clearly, the data clearly shows double periods. It's multiple periods. If it would have been single periodic, it would look like this, because it's a single dot. It's a single time. Okay, what do you plot here? What is the theory curve?
So it's just this simple analytical form. So we have already solved the volume of the droplet, and yeah, it will just this is an assumption of the average time interval. So that's why I told you about this cannot predict. This can only predict the average of the doubling
and
period.
what would you expect your theory to predict? The single periodic or the multi-periodic behavior?
You think this? You're talking about this theory?
Yes, about this theory. What
Yes,
you plotted the graph here, what would you expect it to predict?
Yes,
the single periodic or the multi-periodic?
Yes, because this is the assumption of the time interval for steady drops. So I believe this is for a single periodic as the time interval does not change. So this could be completely applicable for the single periodic.
Okay, then I think your theory clearly mismatches your data, as in the single periodic case, it does not predict it very well, I think. Do you have any theory for why any quantitative theory for the multi-periodic drops?
Yes, I was able to get to analyze the drop formation and the drop oscillation and get the simulation from these equations. Then we're able to get like these black dots as our prediction of.
I think this is only a qualitative agreement.
Yeah. So the main thing I want to prove here is the the critical. So here's the black dot. The black dotted line are the critical that theory predicts, and the blue ridges are the experimental.
Okay, could you please go back to the slide with the black dots? What are these dots here? What are these dots?
These I can't explain. This is just the simulation after these equations. Yeah.
And why does it show these periods down here?
I think it's just because of maybe the assumptions. Because we simplify into only like if we run the full model, I believe we could get a lot without those dots. But we simplify the model into only the two dominant motions. So I believe this may cause some of these to deviate.
Yeah. Okay, but then your theory predicts single periodic here too, and I don't think that you can predict the boundaries. You said that you can predict the boundaries.
Yeah, we can see the boundaries. So,
I'm sorry, if you
these are all like single. Like
I'm sorry, this is not single. If there are multiple dots above each other with this difference, then it's not single periodic.
No, we could look from this part. It looks this is like single.
Okay, I'm sorry, I have to disagree with you here. Good. I would like to talk about more about the jet and how do you define, where do you place? Okay, no. How do you measure the time between the drops?
I take a video from the high-speed camera and then I tracked it. I counted the frames.
And where did you count the drops? Where?
Well,
at what height?
So you talk about what defined as detachment?
No, I talk about you have a video, and where did you count you counted the drops over time?
Yes.
At what height?
Just at the height of the drop detaches.
At the height of the drop detachment. Yeah. Do you think a jet would have played a role there?
Yes. I think from one of the picture we can see the detachment potential. Yeah. The detachment position changes with the flow rate like this.
Okay. And where do you measure? Where do you measure the drop time? Where did you measure it?
Yeah, so like for example, for this one, this is the frame that the drop detaches. So I set this as the frame. And
so you did not keep the height at which you measured constant?
No, yeah, the camera is constant, but I measured the time where it is breaking up, which the time.
Okay, I think you should have either. I think the high-speed video is fine. I think maybe a laser would have been better to measure it. But I think the most important part is that you keep it at a constant height. So that you can.
Yeah, but because it will break up at this height, so I will just record this second.
Yes, but that's why you define boundaries and you say we measure it within this and this regime, so we don't have interference.
Thank you very much for this discussion.
Thank you very much.
So,
I would like to thank the reporter for this very interesting discussion. We first talked about your plots with the single and multi-periodic behavior and what your data showed. I clearly disagree with you, as it does show both in the data and the simulation to have multi-periodic behavior in the regime that you said would be single periodic. So I think that's a very big issue there. And also the theory also predicts multi-periodic behavior in that single periodic regime. And I also disagree that we talked about the critical volume, and I do not agree that the critical volume is constant. I think you did not show sufficient proof, and I think the volume, exactly this one, the volume estimation, I think this is not sufficient proof that the volume is constant, and I do not agree that it is constant in my opinion. And we also talked about your setup, and you explained some unclear points, and I think it was quite good. I would have just liked that you measure the drops times at a constant height. Thank you very much.
Thank you. So now questions from the reviewer to report and the comment.
So first question for the reporter. Did you assume sphericity of the droplets?
Yeah.
Okay, and then did you measure the radius of the vertical radius as well as the horizontal radius in diameter?
I did not. No, most of my report did not focus on like the volume measurements. So only the volume measurement I was talking about is like for this picture.
So okay. So
I believe before detachment it will be a sphere.
So how did you ensure that? How did you ensure that there was sphericity then?
No, I did not.
Okay,
Yeah.
moving on. So then we can kind of talk about. So did you calculate the Lyapunov exponents?
No.
Okay.
Because I cannot plot a phase space for the time interval. Yeah.
So can you go back to your oscillation effect on the drop as well?
I have a lot. Can you clarify which page? Is it
No, sorry.
this
moving
one?
on. Actually, yes. That was. Yes.
Yeah.
Can you clarify that?
Clarify?
Clarify the slide, yes, please.
Oh, so for a single period, we see the oscillation is quite similar. So we can see for two different drops, they have the same curve. But for a double period, we see the two different drops have two different curves. So that's why I believe the two different
Thank
initial
you.
conditions.
For the opposition for slide 29, so what would be your prediction of the relationship of the volume and the faucet diameter?
I think the volume would also increase. I'm not quite sure how.
Okay, so then what's your prediction of the pressure change?
Pressure where?
Pressure, I guess, of the water as it's coming out of the volume, or coming out of that faucet.
The pressure would probably go. I'm not sure.
Okay, so then what's your prediction of, or what's your idea of the relationship between the flow rate and the height of the droplet then?
The flow rate and the height of the droplet. I think when you're in a single periodic regime, you have a constant. You would have a constant height. However, as you get into the multi-periodic regimes, you would the drop height would vary.
Okay, so for the reporter, slide 7, how do you measure the diameter of the droplets? So I'm kind of talking about measurement earlier. So
So I know the tube diameter, and I just compare the pixel width or compared to the tube diameter.
Okay. So do you have any calculated measurement error?
No, but it's just the pixel relation to the length relation.
Okay.
Yeah.
So again, for the reporter, how does the oscillation motion affect the next droplet?
Yeah, so I was talking about when oscillate. So for oscillate, the drop will go up and down. And when it detaches while the drop is going up, it is one condition. And it detaches while the drop is going down, it's the second condition.
Okay, thank you. That's our time.
Thank you. I believe you got 3 minutes for please start your review.
Okay, so this is a review of dripping faucet. Sorry. Okay, so first of all, we've already shared the problem description. So generally, the experiment controlled water level using the siphoning effect, varied diameter flow rate, surface tension, and the viscosity of the water itself. Theory, they used Young-Laplace equation to explain the shape of the drop qualitatively, and that qualitatively explains stable and unstable regions, as well as the chaotic conditions when drops break off from the liquid column. And then they also investigated the Reynolds number and found it to be laminar flow instead of turbulent flow, and then use, of course, the laminar flow model. And then, so then we move on to the data analysis part. They qualitatively explained data based on the shape of the graph patterns. Reporter did well. Thorough explanation of stable region and bipurification. Experimental design using constant flow rate and refilling of the system. And complex understanding of the Laplace pressure and flow inertia. We criticize a little bit and think we could improve upon this. Limited investigation of double periodic behavior, limited mathematical explanation of chaos, and no error analysis. So the summary of the opposition, we talked about only water should be used. Critical volume was not constant, and the multi-periodic behavior was did not match their mathematical model. So, and then the opponent did well, we think. The discussion of double periodic behavior, discussion of the geometry of the droplet height itself. So some of our areas of disagreement. Reported critical volume is constant and decided based on flow rate. The opponent says height of the drops change as flow rate increases, multi-periodic. Our opinion, this is not clear as sphericity was not investigated and only one radius was used to show constant to be critical. So we would like to have seen like the vertical and the horizontal and maybe even a diagonal radius observed as well. Another area of disagreement, so reporter, only single periodic behavior applies, so flow rate versus time. Opponent, multi-periodic behavior is clear and should have been investigated. Our opinion, we agree with the opponent as collected data shows multiple periods of motion, while theory only predicts single periodic motion. So another area of disagreement. Camera conditions remain constant and boundary conditions did not change. Opponent, vertical conditions were not accurate or constant enough. And our opinion is generally we agree with the reporter. I think using the high-speed camera was very clear and for the most part had a very accurate illustration of what was going on. It was very clear. So some missing points we believe. So the sphericity, so in some of those videos, we saw that the drops were not perfectly spherical, so it was, you can see it's kind of like oval. I also kind of want to add that I don't think a sphericity should ever be assumed, and I think you should always, I think you should always compare the your measurements and your radius with like the radius and the volume of a sphere as well, just so you know this is a sphere and my calculations assuming a sphere are correct. So then we move on to there's no calculated measurement error. I understand it's difficult, and I think including this, I'd also like to see how exactly you measured the droplets. I think that was a little unclear, and seeing as the droplets might be a little hard to measure, I think that would have been a lot. I think that would have been a lot helpful to us as watching as well. And and I think the final thing is we have chaotic motion mentioned in the beginning, and it's really not involved in a mathematical model.
Thank you very much. So I want to ask the reporter to conclude the discussion.
Okay, hi, I'm a reporter, and I'm here for the concluding remarks. So the key mechanism for droplet forming is about the surface tension in relation to the gravity. And then the oscillation caused the difference in the initial condition, which caused the difference in the detachment. And I have solved the Laplace pressure for the static shape, and we could predict the critical volume by the geometry of the droplet, and we could get the volume. Then we have the Lagrangian to solve the chaotic regions, where we're able to get a good experimental and theory prediction on where the critical starts of the 3 different regions. Then we're also able to get the drop volume Saturn purification. So for parameters I've investigated, first we'll have the water flow rate stated in the problem statement. And we discussed the critical flow rates of the different 3 regimes, and then the water flow rate increases will decrease the time interval. And we also took a return map to analyze Then for faster diameter, it will cause the difference smaller drop volume and decrease the time interval. They also investigated the fluid viscosity, and because the fluid viscosity will change the drop formation. So that's why even though it does not drip out from a normal faucet, it will change the oscillation, which I think is very interesting. Then also I investigated the hysteresis of the flowing and dripping. Then for discussion, we talk about, I think the critical volume is constant, as we're able to estimate the deviations only about 2%. So I believe the critical volume does not change that much. And the simulation assumes symmetry along the droplet. Then also the tube diameter will change the drop geometry as the width of it forming will be different. And the Laplace pressure is solving for a critical value. And also, when starting the experiment, I made my tube completely full with water. So that's why the smaller hydrostatic pressure could go up in a great height. Then I adjust the position of the metal tube to change the flow rate. Then the steady drop matches the single periodic, the simulation. Then also, the oscillation motion affects the condition for the next drop. And to a reverse question, no dipole of x1 can be measured because no phase space can be plotted by the time interval. And this is the end of my remarks. Thank you.
So are there any questions? Oh, thank you very much for all that. Are there any questions from the jury? So please, opponent Olivia, take the stage. Yes, please.
I have a question to the reporter. So when you change the viscosity with adding glycerin, don't you change the surface tension as well?
Oh yeah, so I have tried to have these are the formulas I found from the reference, and then we find when I change the 40% mixture, it is 600 on the viscosity and only 95% on the normal water. So I believe the tension is not changed that much. So that's the reason I choose glycerol, because the surface tension is quite similar with water.
Yes, please.
To the reporter, how do you distinguish the multi-periodic phase and the periodic phase? How do you distinguish the multi-periodic phase and the
we just find the critical flow rate, and beyond that flow rate, so we look at the different time intervals, and if we can see like two main peaks, this is the doubling, and then after a critical flow rate, we have experimentally find it will just be a complete mess. There's no, yeah.
Are they the same in your work? Multi-periodic and the chaotic, are they the same in your work? In your work?
Oh, they're different. They're different.
Question for the opponent.
Yes, please.
You criticized how the reporter defined like the region where is multiple periodic or single with a single period.
Yes.
How would you distinguish, because you have measurement that differ, how would you instead suggesting to distinguish multi-periodic from single periodic?
Yes. In my opinion, the most important point would be to have more measurement points, and then you would have a higher resolution to see if there would be single periodic regimes and then maybe multi-periodic regimes in between the single periodic, and then it's more difficult. I think you cannot separate it into a single and multi-periodic regime. I think it's much more delicate, and you have different regimes in between.
To the opponent, but do you agree that if you look at the flow rate,
Yes.
there is a difference between the points with low flow rate and high flow rate?
Yes, of course I agree, but there are also, I think there are also double periodic regimes up here. Down here it's mostly n-periodic or multi-periodic. So I think the single periodic are only up here, but period doubling can still occur.
Yes, please.
To the reporter, can you go to the slide number 17? For the simulation, did you make sure that the physics in the simulation is correct? Because I see your the boundary, the beginning of the drop going up.
So,
and can you play the simulation? The animation. Yeah, why it's going up?
Oh, this is just a part of animation. I was unable to finish it, so yeah, just I was unable. So this is just a lot of simulation picture in a video. So yeah,
Thank you.
But this is not like continuous. This is just discrete pictures together.
So
Thank you.
I would like to ask a question to slide number 18, please. So you have your limits. You got your experimental limits where you say it's separated into two phases, and before it was, maybe it was not this slide. You had a slide where you had the three regimes with the experimental prediction and the yeah, this one. How did you get the blue areas where you say, okay, here is the border for changing the regime?
Yes, because I just do my best on making making different fluids, and I just see like I take this point and we plot the time interval to drop number, and this one is the all single, and this one is a double.
So there's no data in between, and you say, okay, here it was this.
So because I have no data in the middle, I think I cannot say there will be a line. I think you'll only have to have a region if I want to be more specific.
So the reviewer, you talk about the Lyapunov exponent. How would you suggest the reporter to do about it?
Well, in entire honesty, I'm not exactly sure how exactly I would add chaos to the model, but I know it is. I'm sure in order to create a more accurate prediction, I'm sure it's very important to add to the model because there is so much chaotic motion as soon, especially when you start getting the more multi.
Okay, thank you very much. Grading.
Can you get through? No worries.
No problem. Take your time. You have to run up or down to make sure it's. Okay, so we finished our grading now, and I want to ask the jurors to show their grades for the reporter. We got 5, 6, 6, 8, and 8. And the grades for the opposition, we get 6, 6, 6, 6, and 7. And for the review, we have 5, 5, 5, 6, and 5. Very much. So for the report, we have, I think it was 2, 8. Maybe you can comment on your 8.
Yes, so I really liked your presentation. I believe your theory was quite well done. I thought that was a real highlight of the presentation. The measurements were a bit, I think you could have worked on the measurements a bit more, especially with you know, making them a bit more easier to understand what do you mean by multiple and single drops. But I think 8 is a really, really good point for the presentation. I really liked it, and I liked your you in the discussion. I like that you always were there to show the graphs. You always had a good, well, you mostly had a good answer. Sometimes I thought that you didn't have, so that's why I gave 2 points. I need to give the points for the partial points.
You can say the partial points.
Yes, so for the report I gave 4.5, and for the discussion I gave a 2. So in the discussion, I think sometimes you didn't you didn't protect yourself enough, so you didn't explain completely well. But overall, I can see that the work is there, so that's why I gave a high point.
Okay, can agree to that. But we have a lower 6, I think, right? 5. Please.
Well, actually, the overall report is very good, but I would say that the only weakness of your presentation is the content, because I see that there is no the explanation about the chaotic regime, and then because you mentioned about the chaos, but you did not talk about the mathematical concept or the physical concept of the chaos. Also that, well, I give you a lot of points during the discussion because you show the data to support your claim and stuff. And for the phenomenal explanation, you show a lot of detailed demonstrative phenomenal explanation. The theory, I don't think that Young-Laplace equation is enough to explain this phenomenon completely. I mean, it's only work for the single periodic regime, but it's like that. And you have the Lagrange model, I mean Lagrange simulation, but you can see that the points scatter and do not give any meaningful result of that. So I reduce a lot of points due to the content, but I also give you a lot of good point for the own contribution because you have some interesting results, but still, I mean, in terms of path movement and stuff, is quite low for me. So the partial point will be 1 plus 3 plus 1.5 and minus 0. So it's totally 5.5, but I wrote it out because of the content.
Okay, thank you very much. So for the opposition, we got, I think I got a single 7, is that correct?
Yes, yeah.
Yeah, so I will comment on the higher grade. My partial grades are 1, 2.5, and 2.5, and no subtraction for the questions. So, well, the questions were more or less the same. That was not the good points of your opposition, but I think you brought in some very interesting discussion points, and they showed and helped deeper understanding within the discussion. So I like the discussion and how you led it. Although some points I would disagree with that you said you see two regimes in the single periodic data dots where they all scattered around one region. So I'm not sure what you meant with this. But overall, I think it was a very good opposition. Maybe I think they were all 6. Am I correct? Yeah. So any one of you wants to comment on that? Yes, please.
So for me, the questions was quite good. I really liked your questions at first, and you lead the discussion after that with these questions, and you present some of your opinions. I would like to hear more of your opinions and disagreements with the reporter. The speech was good, the presentation at the start. So the partial score was 1.5, 2, 2, and don't subtract anything from the answers to the jury questions. So yeah, overall it was a good opposition.
Thank you. And for the review, where were the highest grades?
We had a 6.
I rounded it up because I did everything up this round from 5.5. So I believe that I liked your questions, they were fine, I gave 1 point for that, but they were a bit long. And but I felt during the review that you didn't manage your time very well. Like you finished the bulk of your review in 2 minutes, and then you had 2 more minutes for the missed points. And in the jury sheet, I can give for the missed points at the maximum 1 point. And because of this, I couldn't give points to the other places because you just rushed through it. So for the review of the report, I gave 1.5, and for the review of opposition, it was 0.5 because it was like 20 seconds of 2 things that he did do, but that's not enough for that part. And in discussion analysis, I didn't think that you found all the most relevant points, and that's why I gave 1 point for that. But for the missed out points with the measurement of it being truly a sphere, I gave half point for that.
Anyone who wants to comment on the 5?
Yeah, I can.
Yes, please.
I mainly agree with my colleague. I gave like 0.9 for question asked, 1.5 for review report, 1 opposition, 1 for the discussion, plus 0.2 for missed point out, and I subtracted 0.2 for jury questions. The review was overall good. You showed a certain amount of understanding of the presentation you saw, but I could have given you more if you had focused more on the physics of the matter instead of just something.
Okay, thank you very much. Thank you for this great first stage. And we will meet in, let's say, at 10:20, so in 11 minutes.